Cryovolcanism, often referred to as ice volcanism, represents one of the most fascinating and complex geological processes observed in the outer solar system. Unlike terrestrial volcanism, which involves the eruption of molten rock and gases from a planet's mantle, cryovolcanism operates under frigid conditions where water, ammonia, methane, and other volatiles act as the eruptive materials instead of molten silicates. The presence of cryovolcanic activity reveals that even in environments far from the sun, planets and moons can exhibit dynamic geologic and thermal evolution. This process has been observed or suspected on several icy bodies, including Enceladus, Europa, Triton, and Pluto, and plays a key role in shaping their surfaces, atmospheres, and potential for harboring life. The study of cryovolcanism provides critical insights into planetary differentiation, internal heat transport, and the long-term evolution of icy worlds, demonstrating that the outer reaches of the solar system are far more active than once thought. At the heart of cryovolcanism lies the presence of internal heat sufficient to melt ices beneath a planet or moon's surface. Despite their cold exteriors, many icy worlds maintain significant internal energy, often generated through tidal heating, radiogenic decay, or residual heat from formation. Tidal heating, in particular, is a dominant mechanism for moons orbiting massive planets like Jupiter, Saturn, or Neptune. The gravitational pull from these giant planets continuously stretches and compresses their satellites, generating internal friction that produces heat. This energy can melt subsurface ice layers into slushy or liquid reservoirs, which can then erupt through fractures in the crust when pressure builds up. Such processes blur the line between geologically dead and active worlds, revealing a complex thermal history beneath icy exteriors. The materials expelled during cryovolcanic eruptions vary depending on composition and temperature. Instead of molten lava, these eruptions can release a mixture of liquid water, ammonia water solutions, methane, nitrogen, or other volatile compounds. On freezing, these substances form smooth plains, lobate flows, or domes, reshaping the surface and concealing older impact craters. In some cases, the cryomagma may emerge explosively, ejecting plumes that contribute to thin, transient atmospheres. Saturn's moon Enceladus provides one of the most vivid examples of such activity. Its south polar region is punctuated by fractures known as tiger stripes, from which jets of water vapor and icy particles erupt into space. These geysers not only replenish Saturn's E-ring, but also indicate the existence of a global subsurface ocean beneath the moon's icy crust. The mechanisms driving these eruptions are complex and depend on several interacting factors, including internal pressure, crustal permeability, and chemical composition. Ammonia, for instance, acts as an antifreeze, lowering the melting point of water and enabling cryomagma to remain liquid at extremely low temperatures. Methane and carbon dioxide can also play similar roles, creating multi-phase fluids that expand rapidly when they reach the surface vacuum, generating plumes or explosive releases. As cryomagma rises, it may fracture the crust, forming new vents and channels that can remain active over long geological periods. These processes suggest that cryovolcanism may be cyclical, influenced by orbital variations or gravitational interactions with nearby bodies. Cryovolcanism contributes significantly to the resurfacing of icy worlds, erasing craters and renewing landscapes. This resurfacing provides key evidence for scientists to estimate the age and activity of planetary surfaces. For example, the smooth plains on Europa are believed to have formed through cryovolcanic flows, or upwelling of warm ice, while the young terrains of Pluto revealed by the New Horizons mission suggest ongoing or recent cryovolcanic activity. The discovery of Wright Mons and Picard Mons on Pluto, both massive domes potentially formed by cryovolcanic eruptions, indicates that even small, distant bodies can remain geologically active long after their formation. This challenges assumptions that the outer solar system's small bodies should be cold and inert. Beyond shaping planetary surfaces, Cryovolcanism has profound implications for the internal evolution and habitability of icy moons and dwarf planets. The repeated cycling of volatiles between the interior and the surface can regulate thermal balance and chemical gradients within these bodies. On moons such as Enceladus and Europa, cryovolcanic activity acts as a mechanism for transporting material from subsurface oceans to the surface and into space, providing scientists with direct samples of potentially habitable environments. The detection of organic molecules, salts, and complex hydrocarbons in Enceladus's plumes strongly suggests that cryovolcanic processes are connecting the moon's ocean with its surface, creating dynamic chemical exchanges that could support microbial life. The persistence of cryovolcanism over billions of years implies that these bodies have efficient means of retaining internal heat. Radiogenic decay from long-lived isotopes like uranium and thorium contributes some energy, but tidal forces are often the main driver. For example, the elliptical orbit of Europa around Jupiter creates alternating gravitational stresses that generate internal friction and heat. Similar mechanisms are observed on Enceladus due to its orbital resonance with other Saturnian moons. This heat allows for the maintenance of liquid reservoirs beneath thick icy shells, which serve as sources for cryovolcanic activity. These internal oceans not only sustain geological activity, but also represent potential habitats shielded from harsh surface radiation. The morphology of cryovolcanic features provides valuable clues about subsurface structures and thermal evolution. Domes, ridges, flow-like deposits, and fissures are commonly observed on icy surfaces. Some, like the smooth, flattened plains of Triton, may result from extensive cryolava flows, while others, such as Ceres Ahuna Mons, appear to be solitary volcanic edifices. Ahuna Mons, standing nearly 4 kilometers high, is interpreted as a cryovolcanic dome formed by the extrusion of briny material. Its relatively young age suggests that cryovolcanic processes may have been active on Ceres within the last few 100 million years, highlighting that even bodies in the asteroid belt can exhibit such activity. Modeling cryovolcanic processes requires an understanding of thermodynamics, phase transitions, and rheology under low-temperature conditions. Scientists use computer simulations and laboratory experiments to replicate the behavior of ice mixtures under pressure. These studies reveal that the viscosity of cryomagma can vary dramatically depending on the proportions of water, salts, and volatiles. In some cases, cryomagma may flow like thick syrup, while in others it can behave explosively. Understanding these dynamics helps researchers interpret spacecraft data and predict how such eruptions shape planetary landscapes. Observations from missions such as Voyager, Galileo, Cassini, and New Horizons have revolutionized the study of cryovolcanism. Cassini's detailed imaging and spectrometry of Enceladus provided conclusive evidence of active plumes and heat flux anomalies, while Galileo's observations of Europa's surface showed patterns consistent with subsurface upwelling and cryovolcanic resurfacing. More recently, New Horizons' flyby of Pluto revealed that even distant dwarf planets may retain enough internal energy to sustain cryovolcanic activity. These findings suggest that cryovolcanism may be more widespread in the solar system than previously thought. Cryovolcanic activity also has implications for planetary atmospheres and exospheres. The ejection of volatile materials into space can create tenuous atmospheres or contribute to existing ones. On Triton, nitrogen geysers feed a thin atmosphere, while Enceladus's plumes provide material for Saturn's E-ring. These interactions between surface and space environments demonstrate that cryovolcanism plays an active role in shaping not just individual moons, but also the systems they inhabit. Over long timescales, the escape and recycling of volatiles can alter a body's composition and thermal evolution, influencing its geological future. In the broader context of planetary evolution, cryovolcanism serves as a bridge between geophysics, chemistry, and astrobiology. By transporting subsurface materials to the surface, it creates feedback loops that affect internal heating, crustal renewal, and volatile distribution. It may also influence magnetic field generation by modifying heat flow and convection within liquid layers. Understanding cryovolcanism is therefore essential not only for interpreting the history of icy bodies, but also for refining models of planetary system development. Future missions aim to explore these processes more closely. NASA's Europa Clipper, ESA's JUICE mission, and proposed missions to Enceladus and Triton are designed to study subsurface oceans, cryovolcanic regions, and surface chemistry in unprecedented detail. Instruments capable of detecting heat anomalies, surface composition, and plume activity will provide data to confirm ongoing cryovolcanic activity and its impact on habitability. The combination of remote sensing, in-situ sampling, and high-resolution imaging will deepen our understanding of how cryovolcanism operates and evolves across different environments. Cryovolcanism's role extends beyond our solar system as well. In exoplanetary research, scientists are beginning to consider the possibility of icy worlds orbiting other stars exhibiting similar processes. Planets or moons with strong tidal interactions and volatile-rich compositions could sustain cryovolcanic activity, influencing their atmospheres and potential habitability. Observations of reflected light spectra from exoplanets may one day reveal signatures of volatile outgassing, analogous to that seen in our own solar system's icy moons. The study of cryovolcanism ultimately reshapes our conception of where geological and potentially biological activity can occur. It shows that the conditions necessary for dynamic planetary processes are not limited to warm, rocky planets like Earth, but can exist in frigid, distant worlds as well. By understanding cryovolcanism, scientists gain insight into how planets evolve under extreme conditions, how energy is distributed across different planetary systems, and how environments capable of supporting life might emerge even in the coldest corners of the cosmos.